Yeah, perfect.
Good afternoon, sir. I am Pandiarajan D of SSN Innovatex from Sri Sivasubramanian Order College of Engineering, Chennai, India. This is our work titled BLIP-2-based visual answer questioning with multimodal explanation for gastrointestinal imaging. This is in collaboration work done by Dr. Lakshmi Priya S, Dr. Dhannya S.M., Moogambigai, Nikhil, Karthik S, and Pandiarajan D. Now moving on to the main takeaway. Our main takeaway is from our work is that BLIP-2, a vision language foundation model, can serve as a strong baseline for gastrointestinal visual question answering, but domain-specific fine-tuning and better multimodal alignment are essential for clinically trustworthy explanations. Key contributions of us is that unified framework for answer generation and clinicians-oriented explanations. We have enhanced interpretability via textual rationals, visual grounding, and confidence estimation. Yearly diagnosis of gastrointestinal disorders relies heavily on the interpretation of endoscopic imagery. Visual question answering allows clinicians to interact with visual data using natural language questions, thereby improving accessibility and decision support. Existing medical VQA methods such as MMBirth, PMC visual question answering, and graph-based relational models have achieved competitive accuracy, yet they often lack domain grounding and explainability. Our work addresses this limitation by focusing on the interpretability of predictions, integrating both textual and visual explanations while maintaining answer accuracy. We employ BLIP-2, a vision language foundation model that unifies a frozen image encoder with a pre-trained language model and adapt it to the GI-VQA dataset. Now, seeing our approach, our framework addresses two tightly connected subtasks. Subtask 1 focuses on answer generation. Given an endoscopic image and a clinical question, the model predicts the textual answer. Subtask 2 extends this capability to multimodal explanation, generating both textual rationals and visual evidence for its answers. Technically, we employ a shared encoder architecture based on BLIP-2. The vision encoder, a vision transformer, extracts patch-level representation from the image, and then the text encoder processes the question and fuses it with visual features through cross-modal attention. Training was performed for 5 approaches on GI-VQA dataset using Adam W optimization, a learning rate of 3 × 10⁻⁵, and with mixed precision F16. The model was trained on a single RTX 4060 GPU. This unified setup allows both subtasks to share knowledge while remaining lightweight and efficient. Now moving to the methodology, this is subtask 1 and subtask 2 methodology. Now looking at the results of our subtask 1, our fine-tuned BLIP-2 achieved consistent performance across test splits. It achieved raw score of 0.5 for private test case and meteor score of 0.5 and blue score of 0.2. We found that stable generalization and solid semantic understanding of our model. Overall, this confirms BLIP-2's potential as a robust starting point for medical visual question answering. Now, extending our result for subtask 1, we introduced 3 outputs: textual rationals, visual attention heatmaps, and confidence score. Our model attained correctness of 0.74%, faithfulness of 0.57, and completeness of 0.46. These values indicate reliable localization for prominent lesions with room for improvement on subtual landmarks. And moving on to the lessons learned from our work. Foundation model generalized remarkably well to medical imagery, even without large domain-specific datasets. Domain-specific fine-tuning remains essential for precise medical semantics. Incorporating confidence-aware explanation enhances user trust and provides a practical way to access model reliability. Some inconsistencies still exist between textual explanation and visual evidence, underscoring the need for tighter visual language alignment. These lessons guide how future visual question answering system can become both accurate and interpretable. And moving on to the insights and future work. To summarize our findings, reinforcement that BLIP-2 serves as a unified, scalable baseline for gastrointestinal visual question answering and explanation task. Looking ahead, our next steps include conducting GI-specific fine-tuning using medical terminology, enhancing attention grounding mechanisms to ensure visual faithfulness, integrating domain-adapted large language models such as BioGPT or MediaEval to strengthen clinical reasoning. Ultimately, our aim is to advance towards clinically interpretable multimodal assistance that provide not only accurate answers but also transparent and confidence-aware justifications.
All right, thank you.
Thank you.
Okay. Are there any questions?
Thanks for the presentation. You mentioned in one of the slides that the spatial understanding was not so good. Do you have any ideas why?
Yes, sir.
No ideas?
So can you come again?
I said you mentioned in one of the slides that the spatial understanding didn't work that well from the models. I was wondering if you have an idea why this is the case.
Yes, sir. Our model performs slightly lower in case of domain-specific, like gastrointestinal. It works for general medical visual question answering, but for clinical-oriented, with the dataset provided, our model performs slightly lower. So we need fine-tuning with more extended dataset and with clinical terminologies to avoid this.
It's spatial.
Not really.
So do you have a comment about the spatial information? How it's used in the task?
Why was it so bad to find out where the polyp was?
So can you come again?
Why was the model so bad to find out where the polyp was in the picture? Do you have an idea about that? I can put it in the Discord sheet.
Okay, yeah, look, check the Discord. Check the Discord later for your question. You can answer there.
Yeah.
Okay, ma'am.
Thank you.
Okay.
Thank you.
Thank the speaker again. And on to the next presenter. So